Alright, time for another draftphysics.com, debatephysics.com also. But debate, like at Wikipedia, is impossible. And people won't actually debate specific sentences you could speak about reality and attempt to use evidence and facts as a way of deciphering whether it's a complete or an incomplete statement, whether it's partially right, completely right, absolutely right, all of that. So Newton's laws provide an interesting bit of stuff, okay, because I could argue that there's laws and there's rules. Which the better jargon? So we'll go over the laws and how they're stated, and it's provides some interesting point of view, kind of an absolute statement kind of thing, and can it be argued? And I would argue that certainly it can be argued how complete the statements are. So here's the first law. Okay, this is Wikipedia's translation of the English translation. So it's kind of funny that they don't just put the English translation, they paraphrase the English translation. For what purpose, I don't know. All right, a body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by a force. Now, the simple confusion I would argue that creates is the idea of what's a force. There's two things that can happen to something, right? Radiation can hit it, stuff going the speed of light, or material objects can hit it, bullets or vapey things. They can get hit with a ham or a bologna, pissed off wife. Or they can get hit with an actual, speed of light, piece of energy, like a piece of gravity or a piece of magnetism or a piece of electricity, something moving the speed of light. So there's only two things you can interact with. You can't interact with empty space, so you can only interact with stuff going the speed of light or something going much slower that has been hit by, at some point, has collected something called force. So technically, saying acted upon by a force is correct, but it creates the opportunity for self-deception, if you want to call it that, in the sense that if somebody doesn't know that material objects are carrying force, then they wouldn't know that it's only the force part that you can collect. If a bowling ball hits me, I'm not collecting bowling ball. I'm not collecting its mass. I'm collecting the velocity of its mass. I'm collecting its motion. I'm collecting the stuff pushing the mass. All right. And so that would be I'd say a technical distinction. All right, so the second one. The net force on a body is equal to the body's acceleration. So this is a trick word. Okay. Multiplied by its mass. All right, so he's saying this. Wikipedia is saying that the second law is saying momentum, or equivalently, the rate at which the body's momentum changes with time. When, yes, that's the object, that's the statement, is force equals momentum. It's that simple. All right, and basically saying there's an equivalency, and in the sense, and then Newton states that twice the force, twice the velocity, which means twice the momentum. All right. So you can interchange force and momentum. So it isn't F equals ma. So I don't know why they didn't put their famous F equals ma here and say that's the paraphrase, because that's what they claim Newton said when Newton didn't say that. So he's basically here, they're basically conceding that Newton's just talking about momentum, and he's basically saying there's this equivalency between the idea of force and the idea of momentum. The momentum is force in a different form. Okay. And the argument would be I would argue that the force has momentum. Light has momentum. That light is mass. It's just very small masses. So they're really saying that a lot of little things is the same as a lot of as a few big things going faster. A lot of little things going fast is the same as a big thing going slow. there's an equivalency. So the force is what really carries movement, and matter merely collects that force, the movement. All right. The third law. If two bodies exert forces on each other, both forces have the same magnitude but opposite directions. So everything has a pressure, you could argue, and anytime it comes in contact with something else, it's going to tend to share the pressure. And that's all you really have to say. It's really just saying, I can give away what I have to something else. So I can be one of the little Newton's cradle balls, and I can crash into something, and I can give it all of the stuff I had, right? So I have the force, the motion. Okay, I gave it away completely, and then it gives it back, and then I give it back, and then it gives it back. And it's an exchange of everything that was my motion. So it's a complete exchange of the force. So in that sense, you can give away the force that you have, but you have to have it to give it away. And the contact is the key point. If the contact isn't complete, then you won't have a complete transfer. So if I'm a 7 and I bang into a 5 and we don't hit each other very long, then maybe I should say an 8 and he's a 4. Then maybe all we're going to get to is I'll go down to a 7 and he'll go up to a 5.5 or something, depending on the difference in our masses. So you can give away everything, or you can give away part. You can exchange. But it's kind of like the same thing as charges or something else, where you're really just calculating how much the one thing has to, when it gives it to you, it loses what it had. And it's really that simple. How much ink bleeds into some place where it can bleed means the ink is that less dense. I mean, you're losing something real when you're exchanging with something else. You're either gaining force, or it's losing force, or you're giving away force and it's collecting force. All right. So then they just say a little blah 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 here, and then they say a bunch of other blah blah blah, and then do this nothing math talking about doing these integrals to get to, to try to measure a velocity that's infinitely small. Which, why would you try to measure a velocity that's infinitely small? You never need to know a velocity that's infinitely small. So it's all just, creating artificial limits on their math so it doesn't go to infinity, so it doesn't go to 0. I don't know why all that is in here, okay, but it is. And there's a little bit in here where they show the squared function, I think. I thought it was in one. Yeah, over here. Here's where they start messing things up. So then they come to the conclusion. Consequently, the acceleration is the second derivative of position, often written. So this is just their contrivance. The d over ds, which is d over the distance you traveled, over d, which is the instantaneous amount of time. So I could take any distance and any amount of time. So that's all that means. And there's no reason to write it this way. There's no reason to create squares. It doesn't give you any better answer. So instead of saying 2 plus 2, they're saying 4 plus 4. I mean, there's no reason to do it. And that's where the math goes south, of course, as soon as they start squaring something like a time interval. All right, so the first law is just so bad. I marveled at just what a preposterous pile of nonsense this bottom paragraph is. All right, so translated from the Latin, Newton's first law reads, every object preserves in its state of rest. So let's just say its state, or uniform motion. So he could just say in its state, okay, period. In a right line, so there's no right line when you're not moving, right? So obviously in your state of rest, there's no right line. So, it just makes it more confusing. State of rest, or uniform motion in a right line, except insofar as it is compelled to change that state. So again, it's exchanging a state. It's a real exchange. If you hit something that's moving towards you, it's going to be very different than something that's standing still. So it's not just that you're going to get changed, it's that you're going to exchange. So it's an exchange of state, okay, by forces oppressed thereon. So again, forces is ambiguous in the sense that forces that are being carried by matter, electrons and protons, or force in the form of gravity or magnetism or photons or some other thing moving the speed of light. And there should be a distinction to point out that the matter is a force carrier. The force is the force. The stuff moving the speed of light is the force. Hunks of matter can carry the force. All right, Newton's first law expresses the principle of inertia. So says you. Okay, so it says here, the tendency of objects in motion to stay in motion, objects stay at rest, unless a force causes the speed or direction to change. It's one of the fundamental principles of classical physics as described by Isaac Newton. So they're saying inertia is the second law. Somehow the second law is something called an inertia. All right, and I would argue that why would you call inertia? Why would you call something that could be going, half the speed of light the same word, okay, as something not moving in any direction? All right, the natural behavior of a body is to move in a straight line at a constant speed. So there's the idea that the speed is constant would mean just that you're getting hit by 1 unit of force, but obviously things are hit by a lot more than 1 unit of force in a direction. So, it's not very useful, because I would argue that very few things are ever moving at a constant speed. That is, every time you acquire velocity, you move into the environment, and your speed is going to be reduced just by moving into the environment. There's drag in the space itself, in the sense that the space is full of energy, and every time you, as an electron, move into that energy, it's going to change you. Anyway, the body's motion preserves the status quo. Okay. So it doesn't do anything. It just waits to be changed. So it doesn't change unless it's changed. So until something hits it, a piece of force or a piece of matter, it stays what it is. It keeps doing what it was doing. But external forces can perturb this. So the whole point is obviously change is the word, not perturb. So completely alter, smash to bits. So the change can be tiny and subtle, or the change can be dramatic and catastrophic. All right, so this is where this paragraph is just such a lie. The modern understanding of Newton's first law is that no inertial observer is privileged over any other. So obviously Newton didn't think there was any such thing as observers. There's one three-dimensional blot of space, okay, and everything's in a place in that space, and there's no frames, there's no bullshit. Everything has to move through the space, distance is real, and there's no frameability. Okay, the concept of an inertial observer makes qualitative the everyday idea of feeling no effects of motion. So change in motion is what it should say here, right? Feeling no effects of motion is the wrong thing to say. You say once you're moving, okay, then everything's moving at the same speed, and you can't feel it, obviously, because one piece of you isn't moving any different than the other pieces of you. And you can only feel something when you change how they're moving, right? I have to move my tissue to feel my tissue move. So if you're not moving anything, because everything's moving at one speed, then everything's comfortable and you don't feel anything. But if I change the speed, then I'm going to change it unevenly. The speed isn't going to change evenly. So I'll be like in the car smashes into something. My body's, all the pieces are going, and they're going to keep going. And then I'm going to start hitting things. The windshield or this or that, and break my arm, break this, break that. So pieces of me will start changing. But the whole system doesn't know it's supposed to change. So you only break the pieces that have contact first. So the contact, the deceleration isn't as consistent as the velocity. So the velocity is constant, but the deceleration won't be constant. Different parts of you will be decelerated vastly different rates of other parts. All right. For example, the person standing on the ground watching the train go past is an inertial observer. So says them. So Newton wouldn't go with any of this crap. If the observer on the ground sees the train moving smoothly in a straight line at a constant speed, then a passenger sitting on the train will also see an inertial observer. So, so they're just saying they're seeing each other. And kind of obviously, you know, we can tell which one is actually moving because there's smoke coming out of the train. You know, we know the wheels are turning and all that kind of crap. The train passenger feels no motion. So again, as long as they're going at constant speed. So again, that has to be, you know, emphasized over and over again, that the feeling thing just has to do with the fact that all your parts are moving at the same speed. And if they're all moving at the same speed, you can't feel any difference. Okay. Will also be an eternal observer. The train passenger feels no motion. So again, well, you know, anybody who's ridden on a train knows that you do feel the motion, though. So that's a big lie, right? I mean, in the sense that the train does constantly accelerate and decelerate. It's pretty sloppy, and it's bouncing and rattling and shifting back and forth, and so there's lots of shit going on. The principle expressed by Newton's first law. So this, they're saying this, which is kind of amazing. So in Newton's book, he doesn't get to these laws. He first talks about the bucket experiment, where he's disproving this very idea of a inertial frame crapola, where he's basically saying there's only one frame and there's only one real moving object in space. Newton believed that this is a place in space right here, and things can move in the universe, but this place in space doesn't change. It's always the same place, and it just doesn't matter what you're doing. There's no way you can frame your way out of being a distance from this piece of space. You can't make frames change how far away you are from a piece of space. So this is exactly the opposite of what Newton was saying. I mean, it's just amazing that they put this crap here, okay, when Newton was proving exactly the opposite point, that there is no idea that motion is just relative. He's clearly stating space is absolute, okay, and all motion is relative to that absolute quiet, that absolute fixed position in space. So it's a direct contradiction of what Newton was saying. The principle expressed by Newton's first law is that there is no way to say which inertial observer is really moving. So the whole point of Newton's bucket experiment is to say, yeah, you can prove which one is moving. Especially with spinning objects, it becomes kind of obvious that there'll be physical changes that can't be accounted for if you spin the whole universe. There's facts that make it irrefutable. Now, I've argued you could do things with trains where, yeah, you could put different masses on them and have the masses hit each other, and you'd know who's really moving, because if the three mass going 10 miles an hour hits a one mass, you're going to get a different outcome than if a one mass going 10 miles an hour hits a three mass. It's in a different amount of energy. All right, really moving, and which is really standing still. One observer's state of rest is another observer's state of uniform motion in a straight line. And so this is exactly what Newton did, opposed. And they said this. This sentence is just an amazing perversion of Newton. And no experiment can deem either point of view to be correct or incorrect. Newton's whole point of starting his book with this first argument, the first argument in his book is about the fixed nature of space, okay? And the fact that the three dimensions are relative to that fixed space. And here they're saying no experiment. And what Newton was saying, exactly the opposite. Here's an experiment, the spinning bucket. The water rises, and it kind of proves that if you spun the whole universe, the water wouldn't rise. So if I create some other motion and say the observers see the same thing, yes, they'll see the same thing, except the big difference will be the water isn't going to rise. So I make the observers see the same thing. The universe spinning this way, or me spinning this way. The observers see the same thing. But the fact is, if the universe is spinning, the water's not going to rise. And if I'm spinning, it is. So his whole point was to say, that ain't right. And so he sits here, there's no absolute standard of rest. So I don't know, where could they possibly pick this perversion up? So some Jose and Salaton. Newton himself believed that absolute space and time existed, but that the only measures of space or time accessible to experiment are relative. So that's not what he was saying. He was pretty much saying, look, this experiment proves, okay, that you can do an experiment and it's not a relative problem at all. It's an absolute fact that spinning objects pretty much debunk any notion that space isn't an absolute reference. That's the only observer that's relevant, is what is space? What's it doing compared to a place in space? And that was Newton's argument. So what a perversion. Just amazing that they would claim that Newton's first law implied this nonsense. The very simple idea that you're going to be doing something and you're going to keep doing it until something else causes you not to do it anymore. Somehow that law implies this crap about how there's no legitimate observer, that it's all relative, that nothing is absolutely doing anything. When no, that's not what Newton was saying. It's just so bad. All right, so second law is where we're going to get into all the crapomatics, where they find some way to pervert the truth and imply that he wasn't completely about momentum and momentum alone. So we'll get to that. I suppose I should maybe just illustrate one more. I mean, Newton provided even more than one experiment, so he kind of, pointed out that you could do the same. You could point out the same problem with spinning objects and any notion of relativity by constructing something like this. Okay, this isn't exactly Newton's suggestion, but it's mine. So if you created a hinge here, okay, for two stiff arms, and then you had a very light spring, okay, either between the two balls or just between the balls and the surface, doesn't matter. Very, very weak. You need it just to restore it to its original condition. And then you spun this, okay. What's going to happen is these two balls are going to both rise, okay. Now, obviously, if I spun the whole universe, there's no reason for you to believe the two balls would rise, right? So the inertial observer here, spinning, okay, or the observer here viewing, they're going to see the same thing. If I spin this or if I spin this in the counter direction, they're going to see exactly the same universe. And the only thing that's going to be different is this. And it doesn't matter whether there's gravity. See, this one defeats any argument that the bucket needs gravity to rise. It really doesn't. But anyway, I'm just saying it gets rid of some of your fluid dynamic problems, where in this experiment, it's going to work in the middle of space somewhere where there's no gravity. Okay, the balls are still going to spin. As it spins, these are still going to move out because they're at higher velocity, and they're going to be stuck, okay, with the very fact that they're going to put tension on the spring. They're going to move, and they're not going to move if I spin this universe. If I spin the universe, it's not going to change these at all. Can't have any effect on them. And you can sort of understand that it couldn't, just because of the fact that you couldn't somehow create more gravity in those directions by spinning the universe. The universe can't make more light, and it can't make more gravity by spinning it. So Newton had more than one experiment to defeat the exact thing they said he believed in, which he didn't. So it's just really so evil. All right, the change in motion of an object, so the second law, is proportional. Oh, I'll put this back. Okay. The change of the motion of an object is proportional to the force impressed. So it's clearly saying it's the same thing. Okay, force, motion, force, momentum, same thing. You can't change the mass, right, in these examples. So if you're just changing motion, then it's the same thing. The force will be the motion, and is made in the direction of a straight line in which the force is impressed. The motion in the sense of momentum. Sorry, the mass times the velocity. Obviously, the same force hitting a small object will give it a high velocity. The same force hitting a heavy object gives it a lower velocity. But it's clearly stating momentum is the deal and momentum is conserved. Okay. By motion, Newton meant the quantity that we now call momentum. So at least they're conceding. Newton was talking about momentum. He wasn't talking about 1/2 mv squared or worse, mv squared, which depends upon the amount of matter contained in the body, the speed at which the body is moving, and the direction in which it is moving. So, but he's still saying it's clearly twice the force, twice the motion. 3 times the force, 3 times the motion. Those are almost his exact words. In modern notation, the momentum of a body is the product of the mass and its velocity. So why are you doing all of this perverting to draw a conclusion that says something completely different? So they concede what Newton's talking about, and then they'll do this perversion math to sit there and try to turn it into 1/2 mv squared. And they do it, as I pointed out, by these squared terms here that are completely irrelevant. They serve no purpose. You don't need them. You have it right here. Okay? You have the instantaneous velocity, the instantaneous time. So again, but the very idea that you would bother conceptually saying that you have to reduce this to the smallest distance or the smallest time, when you don't. That's like the 9.8 thing. You do it in 1 second. You say, how much force is it in 1 second? I don't need to know how much force it is in a Planck bit of time or something. Some smallest piece of time. Where do I find the smallest piece of time? And why would I want to know in the smallest piece of time if I could even find the smallest piece of time? I just want a reference. So all it needs here is a reference, okay? Some point where you say, yes, 1 second will equal this much. That's all you need. All right. So I'm not going to bother reading this derivative crap. As the acceleration is the second derivative of position with respect to time, it can also be written. And so as soon as they do this, F equals m, then this becomes their squared velocity. So this is where they turn it into mv squared. And they shove the half in front of it because it's half of the area they're creating. So they're creating an area of velocity, right? A square of velocity. And they need to cut that in half because the square is way too much. That volume's too big, so they have to cut it in half. All right. So we'll read some of this, even though it's going to just be jargon. The force acting on a body adds as vectors. So again, there's no way that anything moving could be considered anything other than a vector, right? I mean, Newton already pointed out that you only have 2 choices. You either don't move or you move in a straight line. Those are your only 2 choices. Newton didn't say anything about moving curved lines or doing any of that other stuff. Nothing can move a curved line and some other force pushes it and forces it to move a curved line. It can't do it on its own. All right. So all motion is a vector. It's just ridiculous to say that something can be moving and it has a non-vector motion. And that's what they've done, playing this scalar game, that somehow kinetic energy is a scalar, which is just an invented word, doesn't mean anything. Somehow the energy doesn't have a direction. It's just an amount, a magnitude, but it doesn't know where it's going. So obviously Newton wouldn't ever go for that kind of nonsense. He clearly knew that force has always got a direction and the end. It's momentum. It always has a direction. And so the total force on a body depends upon the magnitudes of the directions of the individual forces. So now we're talking about more than one force affecting something, which just complicates a simple diagram where you're really just trying to say what's the real thing that's making something happen. And Newton's simple argument is there's this force stuff, and it comes in 2 varieties, free, loose, and force attached to matter. And you can have forces interact either by having a force hit matter. Force can't hit a force. Force has to hit matter, or matter has to hit matter. Force can't hit force. So that might be one of the laws that maybe should be in here. I mean, you could have written more rules, right? He could have said space is a real place with real positions and said that's a rule. Okay, and he could have said that there's only 2 ways force can be expressed, and that is free, going the speed of light, or moving a piece of matter. When the net force on a body is equal to 0, then by Newton's second, so we kind of know that the net force on a body probably is never 0. That there's always Sitting in the universe, there's always, every instant of time, there's always more moving, hitting you from one side than the other. Little Browning emotional consequence of being in the universe is that on the smallest scale, your bits are not going to ever be doing the same thing for 2 moments of time. The body does not accelerate and is said to be in mechanical equilibrium. So again, the concept is kind of nonsensical, because we sort of know that even things that don't look like they're vibrating are vibrating, a tuning fork or something. Lots of things can be doing lots of moving and we don't see it. So I would argue right now you're sitting somewhere or standing or doing whatever you're doing, and lots of you is moving. So even the parts you think aren't moving, they're moving. You're pushing into the ground. The ground is actually physically pushing you back. It's actually doing work, pushing you back. The state of mechanical equilibrium is stable if, when the position of the body is changed slightly, the body remains near that equilibrium. So that's just a nonsensical statement, basically conceding that, it's a little bit here, a little bit there. But the whole point is if you really understood physics, I should be talking over here. If you really understood physics, you'd understand that anytime matter moves one way and then moves another way, that it has in fact consumed some force, because if the force was going the speed of light that moved it, that force isn't going the speed of light when it's moving the matter. So that in some respect, all matter, when any piece of matter moves, it's consuming a bit of the energy of the force. All right, remains near equilibrium. Otherwise, the equilibrium is unstable. So I don't even know what that is just such goop. Okay, a common visual representation of forces acting in concert is the free body diagram. So this is just some point where they try to assess a force, which is perfectly reasonable, but in some respects they can't do it right, because they think mg d, distance, instead of mgt, time. So they're thinking in terms of a force acting over a distance rather than a force acting over a time. And it's just about the time that decides how much force will be exchanged, which systematically portrays a body of interest and the forces applied to it from the outside influences. Again, nothing wrong with it in theory, but there's a lot wrong with it if they're recognizing, if they think distance means something and time doesn't. Time decides the distance. It's not distance deciding the time. For example, a free body diagram of a block sliding upon an inclined plane can illustrate combinations of gravitational force, normal force, friction, and string tension. And all of those are kind of vague, right? So the string tension and the friction force are all vague. Okay, it just depends on what I make the surface out of. I can change lots of factors. I can put a little thin layer of oil on that inclined plane and it won't stick ever. It doesn't matter where I put it. It's not staying there. So the whole thing is a kind of, distraction to getting to the elemental function. Add more factors to hide the truth. Okay, Newton's second law is sometimes presented as a definition of force. How could it be anything else? He's basically saying force equals momentum. Mass and velocity runs the universe. He's saying it pretty overtly, i.e. a force is that which exerts when an inertial observer sees a body accelerating. So it's not about what you're seeing. It's about what's happening. Now, obviously, I can't see acceleration when it's towards me at any kind of distance, because I'd have to measure the tiny bit of contraction in its size, and that's not going to be very helpful. So that ain't going to happen. So this isn't about this isn't about observing it. It's about measuring it. Okay, some other statement about force must also be made. For example, an equation detailing the force might be specified like Newton's law of universal gravitation. So they're making that comparison where they perverted that law also by squaring the seconds. For what reason? No good reason. So Newton says 9.8 meters per 1 second. That's the ratio of the amount of force per a unit of time. It's 1 unit of time, you get 1 unit of 9.8 meters per second. That's what you get as an increase in your velocity per 1 second. It's not seconds, it's not seconds squared. By inserting such an expression for F into Newton's second law, the equation with predictive power can be written. So obviously Newton did just fine, and he didn't have to screw the seconds. Newton's second law has also been regarded as setting out a research program for physics. So something so simple. He's just basically saying that force is an equal proportion to momentum. That you want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. It's very reliable. It works very well. 1 unit of weight, okay, 1 mass, 100 pounds on a scale weighs 100 pounds. 2 100 pounds on a scale weighs 200 pounds, right? Second 100 pounds equals 200 pounds. It's not 400 pounds. Establishing that important goals of the subject are to identify the forces present in nature. Now, that would be okay, right? I got nothing against identity, but I don't think, so this is, why are they implying that Newton's second law says all of this stuff? It's saying something so simple. Force is momentum. And to catalog the constituents of matter. So, again, more kind of just bullshit. We know matter, especially us, we know, but even Newton had some idea that matter was what the thing possessed. The little balls were in there. You know, a certain amount of stuff is in a blob of clay. And he imagined that that stuff had a finiteness to it, that there's some limit. It wasn't infinite stuff. It was a finite amount of matter, okay? And that the matter could move inside, internally, okay? So this is all an idea he had already had. And clearly he was saying that, well, if you see the stuff deforming, well, that's where your energy went. That's where your momentum went. It went to move the little stuff instead of moving the big stuff. The whole thing didn't move, but all the little bits did. All right, so maybe we'll do the third law in the next video. Yeah, so they didn't really overtly say mv squared here, right? They just subtly implied it with an unfinished formula. So they didn't finish this and say, well, this, derives down to, F equals 1/2 mv squared, or energy equals 1/2 mv squared. So, but that's where they're heading. All right, so that's probably enough. And so till the next time and such. But yeah, I mean, laws are nice, but I guess, I'm going to argue that, how they're stated. Again, it's just really about understanding that the force carries all the energy. It's the only stuff really moving. It's the only stuff with a motor. And all it can do is stick to a piece of matter and push it. But the matter is bigger than the force. So for the matter to move really fast, it needs a lot of force to stick to it. It needs a lot of propellers. It needs a lot of little propellers, you could say. So you have some mass, you have little bits in the universe that have little propellers and they can go. And then you have matter, and it's gluey and sticky, and the little propellers can stick to it. Now, if it's already moving in a direction, the rule is a propeller guy can't stick, he has to bounce. And the other guy has to bounce off. So, it's Newton's cradle kind of rules. And all of that should be definable. So I guess I would do it with analogies like currency. I can have $10, and if I give $10 away to somebody else, I only have 5. I didn't need an opposite reaction, right, for me to get to 5. All I had to do was give away the force I had. If I give away the force I have, I automatically have the opposite reaction of going slower. I don't need there to be some rule about it. It's just a fact that when you give away $5, you don't have it anymore. So, that's a harder statement to make, I guess, in one sentence. But clearly, if you give it away, you don't got it. No more. All right. So, till the next time and such, and so forth and whatnot. Despise the world that we exist in with all these authorities telling us what we have to believe and discriminating against us when we disagree with them, shutting us up, cancel culture, just the gross, disgusting cheat. They're afraid of the argument. It's just horrible that we have to live in a world full of cowards and cheaters. And Wikipedia is just like little maggots. It's infested with them. the putrefaction. And that's why they say things that are absolute lies. That Newton didn't believe in absolute space. Yea, did. A lot. He believed in it a lot. Not a little bit. A lot. He started the book with that very argument. All right. Till the next time and such.